The scarcity of freshwater resources and the need for additional water supplies is already critical in many arid regions of the world and will be increasingly important for the future. Today, we'll be discussing the promise of desalination plants and how they can help aid the water security crisis in the future. First, let's establish what we mean by saline water. Water that is saline contains significant amounts, or often referred to as concentrations, of dissolved salts. In this case, the concentration is the amount by weight of salt in water, as expressed in parts per million. So if water has a concentration of 10,000 parts per million of dissolved salts, then 1% of the weight of the water comes from dissolved salts. Our ocean, on average, contains about 35,000 parts per million of salt. Today, there are two main types of desalination technologies: reverse osmosis membrane and thermal desalination. Reverse osmosis desalination uses the principle of osmosis to remove water and other impurities by transferring water through a series of semi-permeable membranes. Reverse osmosis, or RO desalination technology, was initially developed in the late 1950s and has now evolved into the leading desalination technology globally. There are many different processes used in RO desalination, and a variety of factors come into play when selecting the appropriate solution for each situation: the quality of the source water, the desired quantity and quality of the water produced, pre-treatment, energy requirements, and the disposal of the concentrate. In RO, pressure must be exerted on the side with the concentrated solution to force the water molecules across the semi-permeable membrane to the fresh or pure water side. This semi-permeable membrane inhibits the majority of the salt impurities from passing through to the pure water side. The amount of impurities carried over depends on the type of condition of the membrane, such as the age and the cleanliness, and the amount of pressure applied to the process. It's important to note that preliminary water purification includes filtration, clarification, and softening prior to RO applications. The water flows through a two-pass RO system and a demineralization option for further purification. The RO system produces one purified water stream called permeate and a second stream referred to as concentrate, brine, or reject. Feed water enters the machine at a fairly low pressure and flows through pre-filters to remove suspended particles such as silt. A pre-filter is typically a replaceable cartridge type, which provides a cost-effective method for keeping the membrane clean. Typical life expectancy for these membranes is approximately 3 years. RO systems can remove up to 100% of suspended solids and approximately 90% of dissolved solids, dissolved silica, alkalinity, and hardness. It is regularly used for commercial and residential water filtration and is also widely used by boats to desalinate seawater for use on board. RO systems are also capable of rejecting bacteria, salts, sugars, proteins, particles, dyes, and other constituents that have a molecular weight greater than 150 to 250 daltons. The overall efficiency of dissolved solids removal is usually determined utilizing a pair of conductivity measurements, one at the inlet cell and one at the outlet. This is referred to as percent rejection and is calculated by the formula on screen. For example, if inlet water contained 200 ppm of dissolved solids and outlet water contained 10 ppm, the efficiency would be 95% rejection rate. The typical range for this type of two-step RO application is approximately 80 to 100% rejection. It's important to note that reverse osmosis is not limited to the spiral wound configuration shown here. Hollow fiber membranes represent another promising alternative to the traditional spiral wound configuration. The conventional flat sheet or spiral wound RO membranes are usually able to withstand a maximum pressure of about 80 bar. By contrast, the hollow fiber membrane is self-supported and has a higher surface to volume ratio than the flat sheet membrane. The image shown here represents a hollow fiber membrane, which is easier to scale up and simpler in module fabrication than a flat sheet one. Hollow fiber filtration utilizes thousands of long porous filaments ranging from 1 to 3.5 millimeters wide. They're usually potted in place within a PVC shell. Each filament is very narrow in diameter and flexible. Hollow fiber can also find uses in other types of filtration, ranging from microfiltration to reverse osmosis. Hollow fiber filtration works on the same principle as tubular and other capillary configurations, such as the spiral wound design, but utilizes small tube diameter, which allows for greater flexibility. Hollow fiber membranes feature a very high packing density because of the small strand diameter, and because of all this flexibility, certain filter configurations that are possible cannot be achieved in other filtration configurations. Thermal desalination processes account for the other half of the desalination market and consume on average an electrical energy equivalent of 10 to 15 kilowatt hours per meters cubed of treated water. Thermal desalination processes can be further divided into the following subcategories: multi-stage flash distillation, multi-effect distillation, vapor compression, and other processes, including solar, membrane distillation, and freezing. The economics behind thermal and membrane desalination processes must be evaluated carefully in order to determine the best application for a given situation, whether commercial, residential, or municipal. In light of this analysis, the following conclusions can be made. Increasing water treatment plant capacity can have a drastic effect on the overall product unit cost for the end-stream user. Although the initial expansion could represent an increase in capital costs, it can be considered that the economy of scale would benefit a municipal application. Today, the reverse osmosis process represents the best choice for the desalination of low salinity feed water, and this is regardless of plant capacity. The best example is a reverse osmosis plant in Florida, with a capacity of 94,625 cubic meters per day, with a feed salinity of less than 30,000 ppm. Thermal desalination processes represent the optimal choice for the desalination of higher salinity feed water, such as seawater. Multi-stage flash distillation processes will be optimum for capacities higher than 25,000 cubic meters per day, a scale at which most municipalities would be utilized. With the increasing water security concerns around the world, desalination represents a viable solution. Overall access to potable drinking water is arguably one of the major benefits of a desalination plant, the fact that it provides accessible drinking water to those who need it most. This applies even to countries who have fresh water but are experiencing times of drought or natural disaster. In fact, Saudi Arabia gets about 70% of its fresh water via the desalination process, meaning that it's highly beneficial for desert and drought-stricken countries. Desalinated water meets and often exceeds water quality standards. This means that they help reduce the pressure on freshwater sources that may need to be protected. Because these plants treat seawater rather than removing water from freshwater sources, they are preserving habitats for endangered species. Seeing the ocean as a public water supply can even help to promote awareness of the plight of our oceans, further helping sea creatures to live a better life and for rubbish to be dumped more responsibly. Desalination not only provides potable water, but water that's safe for use in irrigation of plants and water for livestock. This is great for arid regions where farmers may not have direct access to a steady supply of water, or areas that are experiencing a drought, much like South Africa or Israel. Because farmers will be able to use the water on their own crops, they will not be reliant on imports and help improve the economy of their own country. They will also be able to produce enough food to sell and feed their own residents, keeping hunger at bay. However, the implementation of desalination plants, especially on a municipal scale, does have its caveats and disadvantages. Opponents of desalination have pointed out that it's not feasible due to the fact that it requires a significant amount of energy to operate. The distillation process requires millions of gallons of salt water to be boiled at high temperatures before it's potable. Reverse osmosis, another membrane process technology, requires a large amount of energy to overcome the natural osmosis process to remove large particles from seawater by using a semi-permeable membrane. As a long-term solution, it might not be best due to the high energy consumption needed for the different processes. Desalination plants can be expensive to build and operate. These costs can run in the hundreds of millions to build and operate, which may not include the equipment and worker training. They can also be expensive to maintain, and these costs are affected by the energy price changes. Operating costs include creating systems and training employees to use the equipment efficiently and effectively. Some studies say that desalinated water is 5 times more expensive to harvest than fresh water, making it too costly for the average consumer. The challenge behind salt disposal and the ultra-brine solution as a byproduct of desalination can pose a significant environmental impact. Chlorine and other chemicals are often added to the water during processing and left behind with the brine, which, if dumped back into the ocean, will bring many harmful substances with it. It can also cause stress and damage to animals who are not used to highly saline water. This negative environmental impact can be remedied with intelligent dumping solutions from engineers who work at the plant. Water managers and policymakers know that desalination cannot be the sole solution to water security. Instead, desalination represents a viable solution to a water security crisis that must be combined with smart water conservation technologies to prevent waste in the agricultural, residential, extractive, and industrial sectors. Water-scarce cities around the world are showing how conservation can be accomplished through a combination of use restrictions and innovative strategies like gray water recycling and wastewater reuse. Humanity will need to use every trick in the book, and a few tricks we haven't dreamed up yet, to ensure a safe and steady supply of water for a growing population. New desalination technologies will certainly be among them. Desalination must be coupled with strong, consistent standards and enforcement to ensure that the costs don't outweigh the benefits.